What is up and welcome back. I am Mr. Shirley. I'm one of the geometry teachers here at Dripping Springs. And today, I'm going to be talking to you about this second set of notes we have here for Unit 10, which is in the subject of probability. Alrighty, so we've kind of seen the basics of probability and how things can be equally likely. We've looked at points in, possibilities of certain things and how rating the probability of something is like counting how many successes there are out of the total possibilities. So we're dipping a bit into, so this is probability. We're still doing probability. But we are kind of dipping our toes here. Probability borrows from this other field of mathematics called combinatorics, which is really where we're spending our time today, the field of combinatorics. How do you combine things? How many ways are there to combine things, right? This is the basics of combinatorics. Today we're going to get started talking about some super cool stuff, factorials. We're going to start using exclamation points in math. Maybe you've seen that before, but it'll be an absolute blast. So at the beginning, we should be familiar with these few things. So it says here you have a coin, a six-sided die, and a full deck of 52 cards. So that's like a standard card playing a deck, a regular old coin, and a six-sided die. So that's a die numbered 1 through 6. So here it says the fair coin gives you heads or tails 50% of the time, right? Equal probability, like with one possibility is heads, the other possibility is tails. Alrighty, and a fair die has 6 equal probability things. And a properly shuffled deck, I like the way it says that, properly shuffled deck would mean any ordering of cards is equally likely. So in the standard deck of cards, there are 4 suits, hearts, spades, diamonds, and clubs. And then there are, face cards and numbers and all that business. So that is kind of where we're starting at today. We're going to look through some cool examples of what's exactly going on. Without further ado, let's get started. So the counting principles. There is a fundamental principle of counting, or the fundamental counting principle, sometimes called FCP. Alrighty, and this is basically like asking, and I would like to start with the example over here so maybe you can see what's going on, but it's kind of like asking how many ways can you do something. So in this scenario, how many ways can you combine 4 different pairs of pants with 6 different sweaters, 5 belts, and 3 hats? Well, that's a lot of stuff to have in your closet. I mean, honestly, maybe not, but we're going to see, even with these 2 sets of clothes, how many outfits are possible. So the fundamental counting principle comes from thinking of this like a tree. If we start here and we say, well, this is my choice. I'm going to choose from 4 different pairs of pants. So in the beginning, you could pick from 4 different pairs of pants, right? Then you could pick from 6 sweaters. So each pair of pants you put on, you could have picked next 6 different sweaters. So you could be 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Wow, this is crazy. I already can't draw it. 1, 2, 3, 4, 5, 6, and so on. You guys get it, right? This one also, same thing. Look how many possibilities there are already. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And then all the way to 24 would be this last branch, right? And that's because there are 6 choices for every 4 pairs of pants. So we can keep going. There's 5 belts on each of these. 1, 2, 3, 4, 5. And I'm just going to draw dots because there's no way I can draw all those. But you guys get the gist, right? Each of those branches would then have 5 more. And then each of those branches would have 3 from there. Wow, look at that. So many possibilities. This is the basic idea of combinatorics, and the fundamental counting principle is how can we count the total, how many endpoints would there be on this little tree? Well, we know that in the beginning there were 4 different choices of pants, and then for each of those there was 6 different sweaters, 6 on each branch, right? And then for each of those there was 5 belts, and then for each of those possibilities there was 3 hats, right? So essentially, the fundamental counting principle says if what you are counting, in this case, how many outfits there are, doesn't depend on other elements of the outfit. So in this case, It doesn't matter what pants you put on. You can put on whatever sweater you want. Now, it may not look good, but you can pick whatever sweater you want with any pair of pants. That would be technically an outfit, right? So as long as all the values that you're counting are independent of one another, that's what goes on here. All right? You can multiply, essentially, to get the result. So you would just, let's see here, and what exactly should I be? And let's see. You can multiply by the number of choices. So, if there are A ways, A the number, if there are A ways for an event to occur, and B ways for a second event to occur, then there are A times B, then there are A times B ways for both of them to happen, for both to occur. All right. So in this case, we have much more than 2, right? But you can see that even if you go more than 2 times, there could be A, B, C, D, E, as many as you want, in any order. You are going to find that you just keep multiplying by the number of possibilities. And in case you were wondering, in the calculator here, let's see. I'm just going to do 4 times 6 times 5 times 3. Oops, not that. 4 times 6 times 5 times 3 is 360 possible outfits. So just with this small number of clothes, there are 360 possible outfits. Now, a good note down here is what it says. And this is kind of what we touched on earlier. And there will be more about this later. So if you're confused right now, just wait. The counting principle only works when all the values are independent of each other. We'll talk more about what that means in a minute. But if one choice affects another choice, so if one choice depends on another, this multiplication process does not yield the correct result. It doesn't work. It doesn't work unless everything is independent of one another. So let's try it out here to find the probability of an event happening. Alrighty? Let's see. To find the probability of a single event happening. Well, what's the event in question, first of all? And then we'll see how many possibilities occur in total. So essentially, and like we've seen, the probability of some event occurring, the probability of E, some event, is the number of possibilities in E. So the number of possibilities that E occurs divided by the number of possibilities in total. Right? And so let's see an example. I think this makes the most sense in an example. Let's try the first one right here. If a spinner goes around a circle and there are 6 red slices, 5 yellow slices, and 3 green slices. Oh, I'm sorry, there's a bunch. 6 red slices, 5 yellows, 3 greens, and 2 purples. What is the probability that the spinner lands on green? Okay, so we'll do green first, and we'll do yellow in a second. Alrighty? So first, what is the total number of possibilities? I like to count the denominator first here. What is the total number of possibilities? Well, the probability that you land on, I'm just going to use G, right? The probability you land on green is the total number of possibilities. So let's see. 6 plus 5 plus 3 plus 2, how many is that? In the calculator, 6 plus 5 plus 3 plus 2. And of course, we could do that in our heads, but we're not going to. There's a total of 16 ways to for anything could happen. There's 16 total possibilities. And out of all those possibilities, there are only 3 chances to get green. So here, this is like the number of greens out of the total on the spinner. Okay? And that looks exactly like what our probability of an event happening is. Okay, let's try it again for yellow. Now notice the probability of yellow is going to be very similar. There's still only 16 possibilities. The spinner hasn't changed, but now we're asking, how many of these are yellow? Well, there's 5 of them. 5 total chances to get yellow. Very cool. For a 5/16th chance. And if you wanted to, guys, you could turn these into a percent if you like, if you like thinking of probability as a percent chance, right? We could do 5 divided by, and here, for example, we can do 5 divided by 16. And this is, if you multiply by 100, 31.25%. So you could think of this, if you wanted to, like a 31.25% chance, but I like 5 out of 16. 5 out of 16 has all this beautiful context. It tells you exactly how many successes there were and exactly how many options there were. So this is my favorite way, and I'm sure your teacher would agree. This is the easiest to grade, easiest to see, like, if you actually understand what you're doing. If you're after the points, fractions are what you should keep. Anyways, let's try the next one. Susie has a bag with 6 red marbles, 5 pink marbles, 2 blue marbles, and 7 white marbles. Bad day for colorblind people in these notes. Find the probability of randomly selecting each color marble. So there are 1, 2, 3, 4 possibilities. So I'm going to divide my little answers here into 4 spaces so I can do it on each. All right. The probability you get pink, and I shouldn't use P there. So PI for pink. Probability you get pink. Well, let's see. There are a total of 6, 5, 2, and 7. Well, let's see. 6 and 5 is 11. 2 and 7 is 9. So there's a total of 20 possibilities. Alrighty. So there's a total of 20, and out of that, there were pink. There are 5 that are pink. And you could, and let me erase here. Thank gosh for my erasable pen. Wow, no way. We could, let's see. We could say this is the same as 1/4. That is true, which is the same as 25%. That is absolutely true. But I don't know, as a probability guy, as a teacher, I kind of like the unsimplified version because it gives you all of the context of the problem. It shows you exactly how many chances there were and exactly how many were successes. But in this case, it may look like there was only 1 pink marble and 4 total in the bag. So I don't know, the context can matter a lot, But I will say these guys are exactly equal. Equals a very strong relationship. They're exactly the same. So if you want to do it either way, probably fine. Alrighty, let's keep moving on. Probability of blue, B for blue. Same thing, there's going to be 20 on the bottom, but there's only 2 blue marbles, which is the same as 1/10. Exact same reasoning there. We could keep going. Probability of, I skipped red in the very beginning. We should do red first. Out of 20. There are 6 total, which is the same as 3 out of 10. And see what I also like, and I'll show that in a minute. We'll say that in a second. And then finally we have probability of the last guy. We got 7 whites. Okay, there are a total of 20 chances out of all of them, right? The bag hasn't changed. But there are 7 whites. So you guys see the difference between these is we're just changing what we're after. Are we looking for pink? Are we looking for blue? Are we looking for white? We're changing, and this actually can't be simplified, by the way. But you can't, don't get caught up on the denominators, right? Like, we're still looking in the same bag of marbles, so the denominator is going to be the same. Now, what I like about leaving the denominators this way, I'm going to go to some scratch paper here to show you guys what I mean. Do you guys see we had a probability of pink, which was 5/20ths. We had a probability of red, which was 6/20ths. And I'm going to show you an advantage of leaving your fractions unsimplified here, is what I'm trying to do. Whoa. Alrighty, and then we got probability of blue, which was 2/20ths, and probability of white, which is 7/20ths. Ladies and gentlemen, what do you notice about the numerator here? These numerators, I should say. Isn't it true? And maybe you can pause the video and think for a second. Isn't it true that 5, 6, 2, and 7 add to 20? Isn't that interesting? So 5, 6, 2, and 7 all add to 20. Why is that? Well, that's because... Oh, wait, what was the last one? 7? Wait, 5, 6, 7, and 2. Oops. Add to 20. The cool thing about this is because those are all the possibilities. So of course, if you wanted to look at getting any of them, right, if you added these up, and we'll talk about this more in a second, you would get 20 out of 20. Very cool. So this is almost it's kind of like a verification that you really have looked through all the possibilities, because look, there's 20 out of 20 right there. All right, let's try the next page. Let's try the next page. We're going to see some dependent examples. So, don't panic. Don't panic. If you see some new stuff, don't panic. Let's see. Combinatorics. And like this is really the last page is also combinatorics, but this is more specifically, I would say more in depth, like combinatorics. Maybe the fundamental principle of counting is not really combinatorics, but yeah, it doesn't matter. So, our first thing here is that we have events can be independent or dependent. All right. What do I mean by this? Independent means they have nothing to do with each other. Whether or not one event happens, it doesn't change the outcome of the other event. So, like, let me write this. Events do not affect the outcome of each other. Do not affect the outcome of each other is what I would say here for an independent event. For example, a good example, let's see, an independent event. Let's see, it could be anything unrelated to each other. So like, let's say, I'll let this example down here. What is the probability of tossing a head on a penny and then choosing an ace from a standard deck of cards? So, let's see, tossing a head on a penny, like that's one event. Let's call it, let's call it PE for penny. Alrighty? Or choosing an ace from a deck of cards. There's another event. Let's call it, A for ace. Alrighty? The probability that these events happen is completely unrelated to what happened in another event, right? Imagine, like, how would it make sense that by flipping a head on this penny, you've somehow increased your chances of getting an ace, or decreased your chances of getting an ace? That doesn't matter, right? It doesn't matter what you flip on the coin. Your chance of drawing an ace is always the same, right? These are independent events. It doesn't matter what penny you get, which flip you get, or if you draw an ace or not. The probability of those don't change. They're independent of one another. Totally unrelated. Dependent events, we'll talk about them more in a second, but they're the opposite. All right, so let's get into independent first. So this notation here, this is a cap in mathematics. It's called a cap, and you pronounce it intersect. So, like here what you're saying is P, the probability of A intersect B. So these are the possibilities that A and B share in common. And so often in math, we just pronounce it as and. P, probability of A and B. So like this event, you can think of this like one event in the middle. The probability that A and B both happen. So that is expanded over here where you guys see we're talking about A and B at the same time. Okay? And the probability that independent events occur, you just multiply them. Very cool, very, very cool. So if it's independent, like in this example, choosing a, tossing a penny and then choosing a head. So the probability that you, toss a head on a penny, all right, and you get an ace from a deck of cards. Alrighty, so this says probability you flip a head and you get an ace. Well, that must be equal to, now they don't affect each other. Now, what I'm trying to say is, I don't know the probability that they happen at the same time. I don't know. But I do know that these events don't affect each other. So you can multiply them by independence. Alrighty, and the probability you flip a head is 1/2. But the probability you draw an ace is 1 in 52. And so, remember, when you're multiplying fractions, it's just numerator times numerator, denominator times denominator. top times top, bottom times bottom, for 1 over 104. There's a 1 in 104 chance that if you toss a coin and then immediately draw from a deck of cards that you would get an ace and flip a head. How cool is that? We've calculated the probability of doing something, pretty seemingly pretty rare. 1 in 104. It's less than a 1% chance, so pretty rare. Very, very cool. Okay. So independent is like the nice, fun land. We love independent. Dependent is where it can get tricky. Dependent is where it can get tricky. So these are events that necessarily affect each other. Affect each other. Like, pretend you were asking yourself, what's the probability that someone wears a raincoat, and the probability that it rains today? Well, those are very dependent on each other. That person will probably only wear a coat in the rain, right? So if you were asking the chances of that, you couldn't multiply those probabilities. It wouldn't make sense anymore. You now need some new lingo. So down here, I like this example. Let's see. And before I get into this, I'm first going to read the example here. Alrighty? So here's the not independent, the dependent event. A bag contains 3 green marbles, 2 red marbles, and 2 red marbles. Sorry. If a red marble is drawn. Guys, I'm crazy. A marble is drawn, not replaced, and then a second marble is drawn. Okay, so there's a bag of marbles. We take one out. Don't put it back. We pull another one out. What is the probability of drawing a green marble followed by drawing a red marble? Okay, so do you guys see, if we were to do this, the first time you draw from the bag, there are two reds and 3 greens. So whenever you pull from the bag, you could get either of these. But the next time you draw, you split the universe into 2 possibilities. Right? After you draw a marble, you could have lost a red. You could have pulled a red marble. Okay? So it could become like this. The bag contents could be 1 red and 1 green and 3 greens. Or you could have pulled a green marble and the red stays and you could add 2 greens left. All right, so what does this mean, Mr. Shirley? What does this mean? What I mean is the probability of drawing a red. All right, oops, sorry, I didn't mean to do that. Probability of drawing a red and a green is not just multiplying them anymore. Instead, we want to find the probability that you were red. Oh, I'm sorry. It's a green followed by a red. Excuse me, guys. It should be G then R. My bad. My bad. The probability you pull a green then a red is the same as drawing a green, then drawing a red, provided that you've already drawn a green. Okay? So look back over here to the notation. I think we're ready to quickly talk about the notation. Alrighty? This little bar is pronounced such that, or sometimes given. Okay? So probability of B given A. Suppose that A already happened. Okay? So, probability of B given A is very important for telling us how to change the problem. So essentially, if A and B are dependent events, the probability of both occurring is the probability of the first and the probability of the second after the first has occurred. So, is the probability of the first and the probability of the second, that's what I meant to say, probability of the second given the first already happened. It already occurred. Oops. I don't know. I don't have enough room to write that, so. Probability of second given the first has occurred. Yeah, it's a better way. Has occurred already. Okay. So do you guys see the similarities here in what we wrote and the notation? The probability of the first event and the second is the same as the probability of the first and the second given the first has occurred. Alrighty. So here you can see the probability of getting a green. Now, so back to our problem. Now, do you guys see there's a total of 5 options? The first time you draw in the bag, I see this as 2 universes, right? The first time you draw from the bag, the probability of getting a green, right? There are 5 total options. So this is probability of G, right? And 3 of those are green. So you had 3 in 5 chances to get a green. But once you draw that green, do you guys see over here? This one is saying you already drew a green. This is the probability of red given that a green was already drawn. Okay? Well, if you already drew a green, that changed the bag. Now, where there used to be 2 reds and 3 greens, can't really fit that in there. There's now 2 reds and 2 greens. So there's now a 2 in 4 chance that you draw a red. The game has changed. Whenever you know something about the problem, whenever something is assumed in probability, it changes the game. Do you guys see? This second bag is distinctly different from the first one. One had 5 options. The second had only 4. And so, same thing here. We can multiply 3 by 2 to get 6. So top times top, bottom times bottom. And 5 by 4 to get 20. A 6 in 20 chance. Okay? Of getting a green. A green followed by a red. Very cool. So my last comment here is about the probability of B given A, which is that last little blank. Sorry, real quick, let me. Alrighty. And so just to clarify here, the probability of an event B given A, this is the probability that B happens if A already happened. In other words, A is given. We already know that A happened. Imagine how much this changes probability. So imagine you're playing a game with your friend and they roll a dice and cover it, and you can't see what number they have. But they peek, and they tell you it's an even number. Hasn't that raised your chances of getting it right? The probability that you guess what number it is just went up, because you know already that's an even number, right? This is the act of changing the game, right? Knowing information and probability changes the game. So these 2 last little things down here, we note that if you are doing some event and there is replacement in the problem, so like in this case, there was no replacement. This is without replacement. All right? If it is with replacement, these events are independent. Okay? If it is without replacement, they are dependent. Because whenever you remove something from the bag in this case, like we had a bag, you've now changed the bag for the rest of the trials or whatever you're doing. Okay? So keep that in mind. Alrighty, for our last little page here, we have a helpful reminder about double counting. So, if you have already made a selection from a group of things, remember, you need to remove a duplicate so it is not counted twice. What does that mean? Okay? To see what I'm saying here, let's look at this example. I think this example is lovely. What is the probability that you pick a queen from a standard deck of cards, okay? And what is the probability that you pick a spade from the same deck of cards? So essentially, if you were to draw one card, what is the probability that you draw a queen or a spade? So I'm thinking of this like probability you draw a queen or the probability you draw a spade. Alrighty? The way you can think of this, what is the probability you draw a queen or a spade? Well, if you looked at the probability of drawing a queen, you might think, well, I could draw a queen or a spade, so that's a queen plus probability of a spade. But there's a problem. The problem is that there is a queen of spades. So here, you've counted the queen of spades once, and you counted it again, because it's also a spade. So essentially, removing that duplicates is the act of fixing the possibilities once you have a problem. So, here, what we do here. The probability of drawing a queen or a spade here is like saying, probability to draw a queen plus probability to draw a spade minus, and in this case, the probability you draw a queen and a spade. So because the queen of spades is a queen and a spade, alrighty, and don't worry if you're not following me, fix it down here, right? Okay, so the probability of getting a queen, there are 4 queens in a deck of 52 cards, plus the probability of getting a spade, there are 13 spades in a deck of 52 cards. Alrighty, but we got to remove the queen of spades because we counted it 2 times. So this gives us 4 plus 13 minus 1, which is 1650 seconds. Alrighty. 16 out of 52 ways to get this queen. Very cool. Alright. So, for the next one, let's try and here. Let's see, where is there we go. So if a bank costs 9 pennies, a bank contains 19 pennies, 10 nickels, 2 dimes, and 15 quarters. If 2 coins are selected at random, what is the probability that you draw 2 quarters? So, I like this problem because it's showing us how we can think of and like multiplication. Well, the probability you get 2 quarters is the probability of getting a quarter and another quarter. Right? The probability you get the first quarter. Alrighty. Now these are, what's it called? You're selecting 2 coins at random, right? So I'm thinking of this like, there are 2 options, 2 possible options of, I meant to say, you're picking 2 quarters. So these are dependent events, because the likelihood you pick a second quarter will go down if you've already picked one. So let's say this is a quarter first and a quarter second. Here's a quarter first. To pick a quarter second, you would have to pick a quarter on the second hand, given you already picked 1 quarter. Alrighty? So the probability you pick a quarter at first let's see. There are 9 plus 10 plus 2 plus 15 options, which is 36. So there are 36 total options here that we could pick from. And 15 of them are quarters. Okay? So there's a probability you get a quarter. All right, now we're multiplying by. If you've taken a quarter out of the group, that leaves only 14 quarters to find out of 35 possible coins. Alrighty. And so multiplying these, top times top, that's 15 times 14, is 210 out of, and then here we have 36 times 35, which is 1260. So there are 210 in 1,260 ways, right? This is your chance. And guys, if you're wondering, you can always do 210 out of 1260. Because I agree, like, these big fractions, yes, that there's more context, but, like, okay, so it's about a 16% chance. Excuse me, I meant to multiply by 100. A 16, this is about a 16.67% chance of that actually happening. Wow, how cool. How cool is that? Alrighty, so let's try the next one with the earn. Now this one is like saying or, okay? So and is like multiply, alrighty? Or is add. Let's see. If an urn contains 9 white marbles and 7 blue marbles, 4 marbles are selected without replacement. The probability of all white or all blue. So let's see what we could do here. So if this guy has 9 white marbles and 7 blue marbles, and we want to pick 4 out of that total, alrighty? How can we tell the probability of all white or all blue? So the probability of getting all white or, oops, let me erase that right, or all blue. Well, let's see. If you're drawing 4 marbles, then you can think of this like, this is a possibility that, what's it called? You get all whites or all blues. Okay. Very cool. So the probability you get all whites, that would be like saying, out of the white group, which is 9, you chose 4 of those, okay? And out of the total possibilities, there are 9 plus 7. You guys see this? 9 plus 7. 16. Choose 4 total possible options. So for the first case, you had 9 options. You chose 4 of those. You had 16. You chose 4 of those for the denominator, plus. And then same thing here. We had 7 options for blue. So 7, we chose all 4 of those as blue. And we had 16, choose all 4 of those down here as well. So on your calculator, alpha F2, to see our little guys down here, we're going to press 8 for NCR. I'm going to see what 16 choose 4 is first. Alrighty. So notice, I see that my denominators here are the same, so I'm going to save myself some work. I see that this is 1820 on the denominator, and then I'm going to do 9 choose 4. So alpha F2 and then 8 again. For 9 choose 4, which is 126. Plus, and then here I've got alpha F2. Alpha F2, and then we're going to hit 8 again. For 7 choose 4 is 35. For a total of, and then we'll add 126, 35. 161 out of 1820. All right. And if we approximate that, 161 divided by 1820, we can see this is about, let's see, we multiply by 100 here, 8.85-ish. And I would rather say, sorry, let me erase this. I'd rather say approximately. This is approximately 8.84% percent chance. So there's an 8% chance about that this would actually happen. Weird. Oh, no, you guys couldn't see. Sorry, that's all I did. Just that right there. Now let's try this last one. Let's see here. A bag contains... So this is a both. Like, this problem is going to require us to break them up and do both. Alrighty. A bag contains 2 cubes, 6 pyramids, and 5 spheres. 2 are selected at random at the same time. Find the probability of 1 cube and 1 pyramid. Alrighty? So, what's the probability we get exactly 1 cube and 1 pyramid? Well, the probability you get a cube and probability you get a pyramid. Alrighty. This is like saying, let's see, so you could think of it like you're drawing them at the same time, right? This would mean you're picking 2 things out of these groups, right? So here we could think there's one way to do it where you got the cube first, right? So you could either get the cube first, then the pyramid, or you can get the pyramid, then the cube. So in the case you get the cube, then the pyramid, that would be like having 2 possible cubes, choosing one of them, all right? And from the 2 possible pyramids, 6 possible pyramids, choosing one of them. All right, and the total here, there are 2 cubes, 6 pyramids, 5 spheres, for a total of 13. So there are 13 choose to ways to do the first thing, but you could add, right? Since there's 2 ways to do it, you can get a cube first or a pyramid second, right? You can also get a pyramid first or a cube second. So getting the pyramid first is like saying 6 choose 1 times 2 choose 1. So getting pyramids then cubes out of the total, which is 13. Choose 2. All right, so notice I'm adding this whole second bar here. All right, and we see, I'm going to save us some math here. So alpha F2, we could do 6, remember it's 8, do 6, choose 1. You guys see that anything choose 1 is just that number. Okay, that's true for everything. So I know this is going to be 2 times 6 over, what is 13 choose 2? Let's do that. Alpha F2, 8. 13 choose 2. Oops, that's 3 choose 2. We're going to go to second insert and make that a 13. For 78. Alrighty, so you guys see the denominators here are the same, so I'm going to add the tops. And then we have another 6 times 2. So we have 12 plus 12 is 24, divided by 78. Let's see, so this is 24 over 78, which is approximately, and let's see, 30.77% chance. Very cool. So, essentially, guys, you can ask yourself, am I replacing, okay, this is like independence. Am I replacing, or am I without replacement? Alrighty, and then and is multiply, or is divide. I'm sorry, add, or is add. Very cool. All right. Again, this is Mr. Shirley. Let me know if you have questions. Talk to your teachers. All that good stuff. I'll see you guys next time for the next video.